We continue our exploration of Arizona's complex water system by looking specifically at Arizona's surface water. We have defined sustainable water as a sufficient supply of water to meet current and future needs for water. We have looked at the complexity of the water supply and demand system at a global scale and discussed the uncertainty of forecasting the future of supply and demand. Arizona has access to 3 major sources of water. It has surface water that exists within the rivers and lakes across the state. Most of you have probably enjoyed some of those rivers and lakes at some point in time. We also have groundwater, which is underground in aquifers. The water table in these aquifers can be anywhere from 10 feet below the surface to 2,000 feet below the surface. So it varies. It depends on where you're at in the state. But groundwater is originally surface water that is percolated down into the aquifers. We also have effluent, water that comes from our wastewater treatment plants that we can reuse. You've probably seen the classic water cycle diagram. This diagram includes water evaporation and evapotranspiration from the land, lakes, and rivers, atmospheric accumulation, which we often see as clouds, eventual condensation, such as rainfall or snowfall, sublimation, which is evaporation directly from snow and ice, runoff water, which flows off the land into the washes, rivers, and streams back down into the ocean. Water also percolates into the aquifers and may flow laterally into rivers and streams. Eventually, of course, water evaporates again from lakes and oceans to go back into the standard water cycle. Here in Arizona, we do have that traditional water cycle. We're close to the west coast, so most of the water we get comes from the ocean to fall onto the desert plains and mountains, and most of our water comes in the winter and falls into the mountains as snow, where it stays there until the spring. Some of it evaporates straight off into the air, sublimation, but most of it melts and flows into our rivers and comes down into the desert plains and lakes, where some of the water evaporates. Some of it eventually flows on down to the Sea of Cortez. Some of the surface water percolates down into underground aquifers, where it's stored and moves slowly into rivers or other aquifers. Shallow aquifers can take anywhere from 10 to 50 years for water to percolate from the surface water to the ground down to the aquifer, and deeper aquifers can take thousands of years. Cities and agriculture use water extracted from lakes and rivers and pumped from underground aquifers. When we're looking at surface water in Arizona, it's primarily focused on the rivers. We have a number of rivers in Arizona, even though we're a desert area. It's kind of amazing how many rivers we have. In the north, we have the Colorado River and the Little Colorado River. In the central part of the state, we have the Salt and Verde Rivers and the Gila River. In the southeastern portion of the state, we have the San Pedro River. In the central western part of the state, we have the Bill Williams River. All waters from these rivers eventually flow, if not evaporated, percolated, or otherwise removed, into the Colorado River. We also have rivers that flow in and out of Mexico. We have several major sources of surface water in Arizona, one of them being the Colorado River. We get our water from the Colorado River Basin, which covers 7 states. It flows through Nevada, then through the northern part of the state, down to our border with Mexico. In most of this basin, water starts as snow up in the mountains, which melts and comes down into the streams, down into the rivers, and then flows across the deserts all the way down to the Sea of Cortez. The allocation of the water in the Colorado River was decided back in the late 1920s. In the lower basin states of California, Arizona, New Mexico, and Nevada, we divided the river's water in terms of the flow at that time and needs determined at that time. California has the largest share, and Arizona the next largest share, almost half of what California has. Right now, water very rarely makes it to the Sea of Cortez. This diagram refers to acre feet. That's 1 foot of water covering 1 acre, so you can imagine about the size of a football field covered 1 foot deep in water. This acre-foot number is the number we use when we're talking about really large amounts of water. How do we get our Colorado River water to populated areas of Arizona? We build the Central Arizona Project Canal, which flows from Lake Havasu all the way down to Tucson. When I say flow, that's not entirely accurate because there are a number of areas where water is pumped from a pumping station to a higher point, then flows downward for a long distance to another pumping station. It takes a lot of energy to get this water to us and all the way down to Tucson, but it goes all the way down to the south of Tucson. Looking at the Phoenix area water supply, you can see how the surface waters are part of the Salt Verde watershed. The Salt River Project has created dams across these rivers, resulting in lakes used primarily for storage. I'm sure you're starting to appreciate some of the complexity of Arizona's surface water supplies. And there's certainly uncertainty associated with the future of these water supplies. When we talk about surface water, we envision that rivers flow all the time and that water is available all of the time, but that's not actually true. In the Southwest, we have wet periods and we have dry periods. This is a graph of the flows on the Colorado and the Salt and Verde rivers dating back to the 1500s. We really only have written historical records for both riverine systems dating from the early 1900s on. The Paleolithic data that you see here were reconstructed from tree ring records. Researchers from the University of Arizona took sample cores from trees and stumps to look at the growth rings to create correlations between tree ring width and river flows from the historical record. Using these correlations, they applied the growth ring river flow relationships to tree ring data to estimate what the flows could have been in the past, prior to the written record. In this 500-year period, prior to 1906, you see estimates of the river flow based on the tree ring data, and you'll notice that the dark blue is when flows on the Colorado River are above average flow. The red depicts below average flows. The light blue in this figure illustrates when the Salt and Verde rivers were above average, and the yellow line portrays when they were below average. One of the first things you'll notice is that flows on the Salt and Verde rivers are much smaller than those on the Colorado River. You will also notice that there are wet periods. The different lengths where the flow within the rivers was above average are illustrated by the light gray areas. You'll see that there is a wet period of about 25 to 30 years long. One of the unfortunate things that happened for users of Colorado River water was that when dignitaries from the 7 states gathered to divide the flows from the river, the system happened to be in a wet cycle. We negotiated agreements to to allocate the waters of the Colorado in the 1920s during a period of high flows. At that time, the method to reconstruct flows was not known, so at that point, the designated spokespersons for the states assumed that the flows in the 1920s represented normal flows. Unfortunately, that wasn't the case. The average flow on the river was actually much lower than that, so the agreement over-allocated the water in the Colorado. As a result, to this day, we over-allocate the river. You'll recall from our earlier presentation that we use climate models to try to estimate what's going to happen to weather and climatic conditions over very long periods of time. This figure illustrates a summary of many 21 models that attempt to estimate what's going to happen in the long term with precipitation. The dark brown areas are where precipitation is going to be less than it has been in the past. The dark green areas are where it's going to be more than it was in the past. Unfortunately, when we look at both annual winter and summer seasons, the Southwest appears to always be in this target area for lower precipitation than historically observed. But as mentioned, we have precipitation estimates from 21 different models. One of the reasons that there are so many models is because it's very difficult to predict precipitation, and in general, the models don't agree with one another. This graph depicts how well the 21 models agree with each other. In this figure, the dark brown to red indicates that none of the models agreed, and the dark green represents those areas of agreement among the models. You will easily notice that for the wetter areas predicted in the northern latitudes from the last graph, the models seem to agree that it's going to be wetter than it has been historically. However, for all the brown areas, the models suggest a high level of disagreement. The Southwest, including Arizona, are in that target zone of disagreement. Even though on average the models indicate a drier future, they don't agree on that. In fact, some of the models for Arizona suggest that it's going to be wetter here. Not many, but some. And it's highly uncertain what's going to happen in Arizona regarding precipitation. Most likely it's going to be drier, but it could be wetter. What's more important is that you can see that the headwaters of the Colorado River, including southern Wyoming, northern Colorado, may be wetter in the future. There's more possibility that that area will get wetter, though it could be drier. There's a lot of uncertainty about what will happen in the future regarding precipitation for the Southwest.